sometimes things come up and I just have to talk about it. And here we have this news story, this post on Twitter from Elon talking about a car that would go from 0 to 60 in under a second. And I don't know much about it. I don't know if it's possible. I'm just going to do some calculations and we're going to just see what we can get. Okay, so here you can see this post right here. 0 to 60 in under a second. That's an interesting point. Blah, blah, blah. Radically redesigned, another car like this. And then people were saying there were some things about like maybe there's going to be rockets on there or something like that. But let's just say why there would be rockets and do some basic calculations. So let's jump over the paper, do some calculations, maybe do some Python. I don't know where this is going. I'm just going free on this. Okay, this is how I approach things. It's going to be fun. Let's switch to the paper and let's just do some very rough calculations. I do need the conversion before I forget. Yeah, I want to convert. Let's see. Let's convert this in here. 1 mile per hour in meters per second, because I want to deal this. So I'm gonna write that down. 1 mile per hour equals 0.447 meters per second. Okay, I'm gonna need that. So we're back over here. Tesla. Okay, jump into the paper. I don't know why I switched over there. Sometimes I just do stuff. There's no reason. Okay, focus. So let's suppose that I have a car right here, and it starts from rest, and there's my road. So V0 equals 0 meters per second. I'm dealing with this in one dimension, okay, so I'm not going to use vectors. And over here, V final equals 60 miles per hour, which I can convert. It's going to be, I can say this is going to be 0.447 meters per second divided by 1 mile per hour, right? That's my unit conversion right there. Since I know that 1 mile per hour is that, the miles per hour cancel, and let's just I have a calculator. Look at this. Here's my calculator that I found. So let's just get a number for that. 60, put it right here so you can see. 60, enter, yes, this is Hewlett-Packard, so it's RPN. And then 0.447 times, I get 26.82 meters per second. So that's my final velocity. And then my delta t is 1 second. So let's calculate the acceleration as the change in velocity with respect to time. So that's just going to be v final minus v initial over delta t. And that's going to be 26.82 divided by 1 second, or 26.82 meters per second squared. That seems crazy. I mean, let's just say is that right? Let me just double check. 60 miles per hour in meters per second. Just jumping over here. 60 miles per hour in meters per second. Okay, so that is right. 1 second. Oh, I dropped my pen. If you double that to 2 seconds, which would be a reasonable value, then you'd have half the acceleration, which would be still 13 meters per second squared. So these are crazy high accelerations. And right off the top, I'm thinking, how could you have an acceleration greater than gravity? Okay, why would I think that? But obviously you can. Now I'm kind of confused, because let's say I have a car with wheels, and let's just draw all the forces on that car as it's accelerating. I have the downward gravitational force. I'll write this as a vector, mg. I have the upward normal force, n. And then I have what makes a car accelerate. What makes it go forward? It's the friction between the tires and the road. So I'll put that this way, F friction. Now, our normal model for static friction is that the magnitude of the frictional force is less than or equal to a coefficient of static friction times the magnitude of the normal force. And this, I looked it up. Mu s it depends on the two materials. For a road, it's going to be in between road and tires, 0.4 and 0.7. So that tells you how sticky it is. Okay, but let's just say that we have 0.7. Let's just say that for now. And you can have higher than that. You can even have, it is technically possible to be greater than 1. But let's say that we have that. And I put that in right here. Then I draw my Newton's second law in the x direction. I can say F net x equals the friction force. That's the only one in the x direction. And that's going to be the mass times acceleration in the x direction. And I'm using scalars because we're in the x direction. And if I put this as a maximum frictional force, then I have mu s, the coefficient of static friction, times the normal force equals ma. Now, in the y direction, I can say F net y is going to be the normal force minus the gravity, the gravitational force, and that's equal to 0 because there's no forces in the y direction. And so the normal force is equal to the weight. In this case, be very careful about that. If I use that over here and plug it in, I get mu s mg equals ma. So now I can calculate the acceleration. A equals mu s g. So let's just put that in as 0.7 times g, which is 9.8 newtons per kilogram, but same thing as meters per second squared. And this has no units. So if I do that, I get 9.8 enter 0.7 times, I get 6.86 meters per second squared. So using that alone, what would be my maximum acceleration? What would be my time to 60? So if that's my acceleration, A equals 6.86 equals the change in velocity. Same thing, it's still the same change in velocity, 26.82 meters per second squared divided by delta t. So delta t is going to be equal to, if I solve this for delta t, I get 26.82 divided by 6.86, and that is going to be equal to, let's just drop that. 26.82 enter 6.86 divided by, I get 3.9 seconds, which is, quite fast. Now there's a lot of talk about like how does a car accelerate, right? What are the limiting factors? If friction is your limiting factor, then that's as fast as you can go. That's the lowest time that you could go with that. Of course, if you increase the coefficient of friction, let's say 1, then this would be 9.8, and the time would be, let's just do that, 26.82 9.8 divided by, I get 2.7. So 2.7 would be the max if we just use normal ideas of friction. Well, how could you increase acceleration? There's a couple ways you could do this. If you don't want to change the tires, let's say I don't change the tires. So let's say I still have mu s is 0.7 for the coefficient of friction. And here's my car. And there's my wheels. Okay, so I want to I'm only accelerating because of friction. So I have my friction force right there, F friction. So I need to increase that. Well, I can't change that, but I can change the normal force. Okay, so one way to do that is to have the gravitational force pushing down. If I increase the mass, that's not going to help, right? Because right here you can see that the mass cancels. So increasing the mass of the car doesn't really help or hurt. But what I want to do is to increase N. So I want to have N greater than mg, and that's going to make this greater. But that means that the car would accelerate up, and in order to prevent it from accelerating up, I need some other force, FO, something else pushing down. So I need something pushing down. Imagine that I had a car. I could just push it with my finger. Actually, here's a car. And this is a good example. This is a little pullback toy. Sometimes if you just push it back, you can get the wheels to slide. But if I push it back while pushing down, I can get it to roll back correctly. You see? And that's kind of the idea here. What if you were pushing it down? Now, what are you going to push it down with? It can't be weight. It can't be an extra weight. It could be rockets, or you could, add a rocket on the end that would push, and then you don't have to worry about friction making it move forward. A rocket car doesn't need that. I suspect, and I have to look this up, and I apologize for not even thinking about this, but obviously a drag racer must have a coefficient of friction greater than 1 in order to have high accelerations. So there's that. But what can we do for this force? Well, one thing is to use something like not necessarily a spoiler, but some kind of air resistance. So imagine that I have a car. I'm going to draw my car like this. And it's moving along with some speed. I have the downward gravitational force, mg. I have the upward normal force. I have the friction pushing it forward. And then I have this interacting with the air. And normally we think of the air resistance as a backwards pushing force, but maybe the air resistance goes like this. And then I have, so maybe the air pushes down on the car to increase the friction. Now that is a problem though, because if I push down on the car with air, I'm also going to be pushing back on the car with air. And so I'm going to need a greater friction just to keep moving forward anyway. So it's kind of a big problem, and I'm not really sure how to address this issue. I mean, this has to push down more than it does forward in order to get any benefit from it. Which I guess is possible. I don't know enough about the direction of that force to make a calculation. But on top of that, this force would be dependent on the magnitude of this. We could say the magnitude of the air is equal to 1/2 rho a c v squared, where that's the velocity. So at the beginning, you're not going to have that acceleration. You're not going to be able to do this because you're not moving and there's no air pushing down on it. This depends on the velocity. The magnitude of this depends on the velocity. I'm thinking like, what if you don't have to have a constant acceleration. It's possible that your velocity as a function of time could look like this. So this is the maximum acceleration right there. That's the slope of a line with, let's say, well, what did I calculate for the acceleration? 6.8, or let's even say 9.8. Let's say 9.8. So the slope is 9.8. So maybe I start off right here going 9.8, and then as air gets greater, then I can increase my acceleration like that, and that could give me a total time less than. So you want this to be 60, and this to be 1 second. Let's see if we can make this plot. And I'm not even going to have a discrete curve. I'm just going to say the acceleration depends on the velocity, and I want to make a graph like that. So my acceleration is, let's just write up an equation for that depends on the velocity. I don't know these constants and all that stuff. I know that this depends on the normal force, and that pushes back. And then let's say that it pushes down more than it pushes forward. I'm just making up stuff here. So I can do a numerical calculation where I say the acceleration is 9.8 plus some constant c times v squared. I'm going to say that. Okay. Where c, I'm just going to pick. C, let's start off with c is 0.01. And then I can calculate the change in position during each short time interval, delta t 0.01 seconds or something like that. And v2 is v1 plus a delta t. And then I can calculate the new position, x2 equals x1 plus v2 delta t. This is your standard numerical calculation recipe right there, breaking it into small steps, which I have to do because I have a non-constant acceleration. So let's plot that in Python and see what it looks like and see if it gives us any insight into if this is even possible. Okay, switching over here to Python. Python, where'd you go? Right there. Okay, Python. So I'm using WebVPython. Let's make a graph. G1 equals graph. Make this bigger. Bigger, that's good. Title equals impossible Tesla. Question mark? You like that? X title, I'm going to plot, X title is the time in seconds. And then let's put on the next line, Y title is velocity. And I'm going to convert to miles per hour just because that's what everyone likes to see. Miles per hour, and then let's give it a width of 450 and a height of 200. And then I need a curve. F1 is G curve. Color equals color dot blue. We might add another curve in later. I don't know. Now let's just make our let's just put in our properties here. So I have t equals 0, dt equals 0.001. I'm gonna make it a little bit smaller. If I'm only going to 1 second, I need that smaller. C equals 0.1. Again, I'm just picking a value here. I don't know what it is. I need my x position 0, my velocity 0. I'm leaving off the units. And then let's just run this for 1 second. So while t is less than 1, number 1, calculate the acceleration. A equals 9.8 plus c times v squared. And again, we start off with v is equal to 0, so the acceleration is just going to be 9.8. We're assuming coefficient of friction of 1. Now I can use that to update the velocity. V equals v plus a times dt. Now I can use that to update the position. X equals x plus v times dt. It's an approximation, but if the time interval is small, it's good enough. And then I'm going to plot that point, f1 dot plot tv. I want to plot the velocity. And now I need to update time. T equals t plus dt. Let's run it. I will give you the code at the end. Don't worry about that. Okay, so this, remember, let's draw another line, a 60 mile per hour line. Let's convert this to 60 miles per hour. So I need to divide by, what was my conversion factor? 0.447. 0.447. Let's just, then we can see that a little bit better. Okay, so this one gets up to just 34 miles per hour. So clearly that's not good enough, not nearly good enough. I'm still kind of perplexed because I know cars have a higher acceleration than that, and I don't know how they work. I don't know anything about cars. Okay. So let's just increase our value of c to, let's say, 5. I'm just playing around with this for now. Oh, that's weird. It just exploded. Wow. Let's put it at 0.2. That does look better though, doesn't it? So it is exploding up here because as it goes faster, you get a much greater acceleration. Of course, the problem is that at some point we have a friction limit to the acceleration, and then later we have a power limit to the acceleration. And this is the idea in a drag race, and I need to look at that in more detail, but this is just a first estimate model. I'm just kind of free thinking here. So this definitely would beat it. Let's make that a little bit smaller, 0.17. I can just play around. Oh, I got it right there. Okay, so that was my final velocity. It worked. And then you can see this curve gives me an average acceleration of the same thing, right? The average acceleration of 26. It's just that over here we have a much higher acceleration. Let's make another curve just for fun. F2 equals G curve, color equals color dot red, and this one's going to be the acceleration of an object with the constant acceleration of, what did I say it was? 26.82. So I'm going to make another acceleration. A2 equals 26.82. Wait, is that what I calculated? Yeah, that's acceleration. And I'm going to need another variable to plot. I only care about the velocity, so let's call this V2 is 0. And then down here, I'm going to update V2. V2 equals V2 plus A2 times dt, and then I can plot that. F2 dot plot T V2 divided by 0.447. Let's just see what happens there. Okay, so you see they end up with the same velocity. So this is my constant acceleration. This is a increasing acceleration, but they both have the same average acceleration. They both start with the same velocity. They both end with the same velocity. Okay. I think it's a good physics problem. I think it'd be a great problem for students to work on with these basic things. I definitely need to go look at drag racing and see what happens there and how do we deal with cars going with a greater acceleration greater than 9.8 because I don't know what's going on. But that's that. So I'm going to give you a link to this code down below. Let's see what happens with the Tesla super fast car, super high acceleration, if it even exists. We know not to hold our breath. Who knows? Elon may do something super weird like he's done before, but, you know, he did launch a car into space for really no reason. So there's that. Okay, physics, code down below. Hope you like that. Talk to you later.